All right, so can we start?
Yes, sure. Okay,
okay, let me introduce you first. Okay, so thank you, Daniele, for accepting to give a talk. Thanks everyone for coming. And now we will listen to Daniele Mastrostefano from University of Warwick, who will speak on the partial sum of a random multiplicative function on integers with a large prime factor.
Okay, thank you very much for inviting me and for giving me this opportunity to speak. So I would like to start with a definition, which is the definition of a random multiplicative function. So in particular, we are going to focus on a Rademacher random multiplicative function, which is defined the following way. For any square-free integers n, we define f of n as the product over the prime factors of n of fp, where fp are independent Rademacher random variables. So each fp takes value plus minus 1 with probability a half, and for different p's, we have independency. And we extend f to also non-square free integers by setting f to be 0 in that case. Okay, so this function is thought to be a random model for the Mobius function, and indeed Winter in 1944 introduced a Rademacher random multiplicative function exactly to model the Mobius function, which is a deterministic function defined in exactly the same way, but here we have a constant value -1 on the prime. Okay, why we can think of a Rademacher random multiplicative function to be quite similar to the Mobius function? Well, it's just because they have both multiplicative function, both supported on square-free numbers, and both take values plus minus 1. The motivation to introduce this function was to understand this well-known conjecture that the partial sum of the Mobius function is bounded by x to the power a half plus epsilon for any epsilon bigger than 0. And this is equivalent to the Riemann hypothesis, which is a statement that gives strong information on the distribution of prime numbers. So this was indeed the original purpose of Wintner, who proposed finding almost sure bounds for the growth of the partial sum of f of n, and himself proved that almost surely the partial sum of f of n is bounded by x r plus epsilon, so thus showing that this conjecture might be true. So this is at least in the direction of this conjecture. And it also proved that the sum of f of n is not bounded by x a half minus epsilon, almost surely, which means that the partial sum of f of n almost surely stays large. Okay, but these are the first result on the size, on the almost sure size of the partial sum of f of n. And if you see here, there is a huge gap between the upper and lower bound. So, of course, it's a very interesting problem to understand better the size of this sum. And Erdős refined Winter results by proving that the partial sum of n is bounded indeed by root x times a power of log, and is not bounded by root x times a negative power of log, almost surely. And this is a huge improvement on Winter results, because we have replaced an arbitrary small power of x with a certain fixed power of log. Later, Olas improved this upper bounds to this quite horrible expression, but one has to think that in Erdős result, we have log x to the power a, which can be rewritten as the exponential of a times log x. And here Olas has exponential of a constant times square root log x, essentially. So we have this square root log saving compared to Erdős result. Okay, the Best to date bounds are due to Laut and Baum-Hu in 2013 and mostly independently by Boskin in 2012, who refined Olas's approach and showed that the partial sum of FON is almost surely bounded by root x log x to the power 2, roughly. On the other hand, Harper, improving on his own previous result and answering to open questions posed by Olas and Erdős, established that almost surely the partial sum of f is lower bounded by root x log x to 1/4, roughly. So actually he had much stronger lower bound, but let's say that we have something like this. Okay, so if you look at this upper lower bounds, they are much closer than what we had before, and they have the same structure. They have this root x here, which is almost the typical size of the partial sum of f of n times this log factor. And this kind of result looks like a law of the iterated logarithm type result for the partial sum of f of n. So I would like just to stop a moment to review what the law of the iterated logarithm says. For a sequence of independent random variables, taking values plus minus 1 probability a half, the law of the iterated logarithm says that the partial sum of xn can get as large, almost surely, as root 2x log x, and as small as the opposite, infinitely many times. And actually, this is the more precise statement given by Hinchin. Here is very important to remark that xn is a sequence of independent random variables. And moreover, since for a sequence of independent random variables, which are identically distributed, the central limit theorem says that the partial sum is distributed like a Gaussian with mean 0 at variance x. So it's typically like size like a constant times square root x. Whereas the law of the iterated logarithm says that almost surely it can get large as the typical size times root log x, because it takes into account not only of the value of the partial sums at a single point x, but of the interaction between the different sums on different points. So it's much more stronger information. If we would like to show something like that for random multiplicative functions, well, the situation is much different because the values of fn are not all independent. For example, the value of f at 6 is the product of value of f at 2 times the value of f at 3. So it's completely determined by this. So the classical theory for independent random variables cannot be applied in this case. We might believe, though, the suitable version of the law of the iterated logarithm could yet hold for them, because maybe the multiplicative structure of a random multiplicative function is not that bad. Maybe does not completely disrupt the size of the partial sum, the size of the almost sure fluctuations of the partial sum. However, we don't know exactly what could be the value of such largest fluctuations. But if we might have to guess something, well, by a recent result of Harper, we know that typically the size of the partial sum is root x over log x 1/4. So quite close to what we have in the classical sense for independent random variables, in which case we have just root x here, but we need to adjust by this factor, log x 1/4, that comes from specific object in probability theory, which is related to the distribution of these partial sums. And if we take this typical value and we multiply it by root log x, which is this factor that appears in the law of the iterated logarithm, which takes into account of the distribution of these sums on several points altogether, well, we will get this value, root x times log x 1/4. And this indeed in accordance with Harper's almost sure lower bound that we saw before. Okay, so but how is Harper lower bound proved? Well, the starting point is the following. He realized that to produce almost sure lower bounds for the full partial sum would have been enough to look the partial sum of f over integers with a large prime factor and show a corresponding statement. Actually, he had a different condition here, which he introduced to simplify his computations, but with more effort it's possible to deduce this statement with this condition in place. Okay. This is possible because if we look at the complementary part, which is over square root x numbers, so numbers with a larger prime factor smaller than square root x, well, with high probability, this partial sum cannot be that large to cancel out with this part of the sum. Well, it may be on some points, but at least not over a suitable random subset of points, which is then enough to deduce a lower bound. If we would like to do the same, so to produce almost sure now upper bounds for the partial sums of f of n, trying, for example, to improve on the Baskin and Loud and Baum-Hughes result, which I remind you gives an upper bound of root x times log x to the power 2 roughly for the partial sum of f of n, we cannot remove the contribution from the root x smooth numbers from our argument, because that part could contribute something that large. Okay, but nevertheless, we can focus on this complementary portion and then prove the following result. If f is a Rademacher random multiplicative function, then for any epsilon bigger than 0 and as x tends to plus infinity, we almost surely have that the partial sum of f over integers with a large prime factor is bounded by root x log x to the power 1/4 plus epsilon. Okay, first I would like to say, to make some comments about this result. But first of all, considering Harper's result, we see that this is close to B sharp, because Harper's gave a lower bound for this partial sum, which is exactly of the same strength, apart from a little one factor here instead of epsilon. But more or less, we have same size. So we have this 1/4, for example, in the power of log. Okay, and second consideration is that this gives an indication of the size of the largest fluctuation of the full partial sum, because this set of integers is a positive proportion of all the set of all the integers up to x. So this part of the sum is like a big part in the full partial sum of f of n. And so by considering this and Harper's result that gives a corresponding lower bound for this, well, we might expect that the same might hold for the full partial sum, and that the full partial sum would maybe exhibit almost sure fluctuations no larger than roughly root x log x 1/4. The validity of the previous section is currently being investigated in a joint project with Adam Harper. Actually, I would like to conclude this comment part with a brief anecdote. So I started working on this project last summer, and Adam, who was supervising me, realizing that realized that this studying this sum was enough to deduce the almost sure lower bound that he gave in his beautiful paper. And starting from there, we have been working on proving the same, but for the full partial sum. Okay, so before going more into the details of the proof, I would like to stop a moment in case there are any questions at this point.
Yes, maybe, excuse me. If you look at the sum of f of n about square root of n, do you get the corresponding result, or is it?
So if you look the sum of f of n
upon square root of n.
So with all the integers up to.
Yeah, same summation condition, do you get that it is almost surely less than log x to the 1/4 plus epsilon? I mean, can you call something like that?
With the opposite restriction.
No. Same summation. Instead that you look at f of n upon square root of n.
Oh, okay. So divided by square root of n.
Yes.
Yes, we have similar results. I think that they have been proven by people in the audience.
Okay.
But I don't remember if they are quite of that strength. I think they are not of exactly of this strength.
Okay, thank you.
Or maybe that can correct me.
I think the Bessemer upper bounds with the weight have some log powers on the right-hand side.
Okay, so not definitely of the same strength.
No.
Okay.
Okay, thank you.
Can I ask a question?
Yes, please.
Would you expect that the dependence on the largest prime factor would hide somewhere in the epsilon?
No, I don't expect that. Also because, as I said, Harper lower bound for this partial sum, which is this, gives the same with an little one, let's say, or something even more precise than that. And I would expect the same to hold also for the upper bound. So I would expect this upper result to be quite sharp.
Well, yeah, I understand that, but I meant that if one would try to identify what this epsilon looks like, what's the next order logarithmically, then would the choice of the largest prime factor influence that? That obviously doesn't concern the 1/4 that you have. But maybe it's not clear what I mean.
So you mean if it's possible to deduce a dependence of epsilon in terms of x?
Yeah, would you expect that to depend on your choice of the largest prime factor?
No, it won't depend on that.
Okay. Thank you.
Thank you. All right. So if there are no other questions, I will start with proof. Okay, so this is the aim of the proofs. If we define M of f of x to be this partial sum, and if we fix epsilon bigger than 0 and say L greater or equal than 1, a positive integer, then we would like to bound the probability of this event A sub L, which is the sup over all x, into an interval with endpoints, a very sparse sequence, of the fact that the quotient between M of f of x and this largest size gets large. If we find an upper bound for the probability of these events, which is summable on L, then we can conclude by an application of the first Borel-Cantelli's lemma. In that case, the sum of the probabilities of the ALs will be bounded, and then the probability of the lim sup of these events would be 0, which is equivalent to say that from certain point on, the opposite event, the opposite condition holds. And so M of fx will be bounded by this quantity as in the theorem. In order to do that, we will follow the proof of Lau, Tenenbaum-Wu by defining a sequence of test points xi between this interval, say, so that to discretize this large interval and to look this event on a suitable test points where we might say something on the size of M of f of x. And we would like the sequence to be then close together, but not too much, because we will also like the increments between two consecutive test points to don't grow very much. The specific choice will be, as in Lau, Tenenbaum-Wu's proof, xi to be the integer part of the exponential of I to the epsilon, and the xl to be the exponential of 2 to the power L to the power K, whereas in Lau, Tenenbaum-Wu's proof, here K equals 1, but here we need K to be 1 over 4 times epsilon. Since epsilon is small parameter, K is very large parameter, of course. So here we are looking at a much sparser sequence of points, XL, where this partial sum gets large. Okay. Once done that, we, to understand the probability of this event, we look at the event that this holds on the sequence of test points and between the test points. So first, let us look what happens between test points. If we rewrite a bit this event, where we will need to bound the probability of these two following events. This second one is the supremum for x between two consecutive test points of the partial sum of f of n into a short interval with the condition that Pn is larger than root x. And we ask that the supremum of these partial sums is larger than this quantity, where here for short I wrote r of x as log x to 1/4 per section. So for this second event, well, this can be dealt with as in Lau, Tenenbaum-Wu's paper, because essentially they have the same without this restriction, but this is very mild restriction. So it's possible to adapt a proof to understand this event. The first one instead is quite different, because we have the full partial sum of f over the condition that the largest prime factor is inside the short interval. So we have to do something different to understand this. And actually, if you look a bit to what this is a random variable in which we extract at any next time, we extract a different prime factor. So we are revealing a new prime factor each time. So this is the structure of a submartingale. And indeed, if we look at the square of this partial sum, well, this defines a non-negative submartingale with respect to this filtration. So Fk, which is the sigma algebra generated by all the values Fp for p smaller than square root k. And why is that? Because Fk is an implicit sequence of sigma algebras. Zk is certainly Fk measurable, because the values of Fn are determined by the values of f at all primes smaller than square root k, thanks to this condition here. The first moment of Zk is bounded, and it's possible to prove, it's easy computation, that the moment the conditional expectation of zk plus 1 given fk is at least zk. Okay, so if we come back to that event to understand the probability, we first use Markov's inequality for the power 2, and we get this bound. We get this normalizing factor times the expectation of the second moment of the soup of this non-negative submartingale. And in order to understand this, well, Doomb's L2 inequality gives exactly a bound for quantities like this. So Doomb's L2 inequality says that the expectation of second moment, in this case, of the supremum of a sequence of submartingales is bounded by the supremum of the second moment of the submartingales. And so in this case, we end up with the expectation of the fourth moment. And to understand this expectation, there is a classical way to do it, which is called the rough hypercontractive inequality, which gives exactly a bound on this moment of partial sums like this, in terms of a corresponding partial sums, but of the divisor functions. Here we are using the divisor function for the parameter 3. And this sum can be computed using classical estimates for sums of divisor functions and gives this value. And if you look, the xi minus 1 square will cancel with this one. And we will have log xi minus 1, which is, if you remember the definition of test points, something like I to the power epsilon. So essentially here, when we put this back, we will get a bound like 1 over I squared, which is summable on I, and then we'll give something summable on L as well. And so something that will go into the application of Borel-Cantelli's lemma. Okay, so for the partial sum of f between test points, everything is settled. Now we need to understand the sum on test points. In this case, mf of xi can be rewritten as the sum of random variables yp for primes into this quadratic interval, where yp is just fp times the sum of f of m for integers m at most xi over p. Well, the random variables conditioned on f square root xi, which is the sigma algebra where we take define as this the sigma algebra generated by all the fp for p is smaller than square root xi. Well, all these random variables then becomes fp times a constant, essentially, conditional on the sigma algebra, and so they become independent with conditional mean 0. So m of f of xi is a sum of lots of independent random variables for which we might expect to have Gaussian distribution, and indeed this is what Adam proved in his paper. But here we need much less. Here we just need a bound on the tail of the probability of these partial sums, and Hoeffding's inequality gives exactly that. The probability that m of xi is larger than this quantity conditioned on the sigma algebra will be bounded by this exponential. So here we have the square of the parameter that appears here, and here we have the sum over primes of the square of this random variable. So essentially the sum of the variances. This is why I recalled this denominator as Vxi, because it's a sort of variance, let's say. Okay, in order to understand now this probability, and so to bound the probability that our sum on test points is large, we need to understand this sort of variance here. And indeed, if we assume that this variance uniformly over all the test points into this very large interval is bounded by t times its expected value, we can put this bound back in the previous computation and estimate the probability that MFXI is large over the test points, which will be bounded by the sum over all test points of this exponential. And now we can conclude from this because, well, first remember that Rxi was log xi to power 1/4, roughly. So here I get in the numerator log xi, roughly. And log xi is L to the power k, which follows from our definition of test points. So if we take t, for example, as epsilon L to the power 8, which will be also useful later, then we can make this part exponential as the exponential minus a large constant times L to the power k over epsilon, which plays against this factor, 2 to L to the power k over epsilon, which is the number of test points which are in this interval. And then it's clear that this is summable on L. And it will give then, it will conclude this part on the partial sums over test points, which again will go into the application of Borel-Cantelli's lemma and will conclude the proof of our theorem. But we are doing that assuming that these sort of variances are bounded by this quantity. And this is something that we need to prove, that this, we have to prove that this holds almost surely. Okay, just a last remark about this. Here, you can notice that the choice of Rxi as log xi to the power 1/4 is exactly the minimum choice we can take here in order to make this exponential comparable with the factor coming from the number or counting the number of test points. Okay, so we would like to understand that the complementary event here, that these sort of variances are large over test points. So first of all, we rewrite the variances. This is kind of classical and has been made in several other past works. So first we insert the logarithmic weight into the sum, then we insert an integral to smooth a bit the sum, and then we split the sum, the partial sum of f into the partial sum of f up to xi over t. So it's basically the same because t is close to p, but now it's kind of continuous version. And here we have the partial sum of f of n into these short intervals around the endpoints of this sum. And now we would like to understand the contribution of both this expression and this expression to the previous event, that this sort of variance is large. So we need to understand when both of these quantities are larger than what expected. So starting with the second one, well, again, we apply Markov's inequality to study the probability. In this case, we apply Markov's inequality with the power q bigger than 1. So that we will get a bound like that. So it looks a bit scary, but we have the sum over test points of this normalizing factor raised to the power q. And then we have the expectation of this expression here. Now, if we are able to prove that this expectation is bounded by xi to the power q over log xi to the power q, then inserting this back here, we will get this upper bound, of course. And well, remember that xi is inside this range, which means that log xi is between these two power of 2. So an upper bound for this quantity will be, okay, log xi can be bounded by the reciprocal of 2 to the power L minus 1 power k. Log xi will be roughly L to the power k, and everything here is raised to the power q. Then we have this factor that comes from the number of test points, and then the factor t to the power q. If we choose q very large, like 3 over epsilon, then we can further upper bound this with this quantity, which is easily shown to be summable on L. And so in a certain sense, this contribution to the variance will be sufficient to prove our theorem. Okay, but here we need to prove that this expectation is bounded by this quantity. And what we can notice about that is that this can be viewed as the Q power of the Q norm of this expression inside parentheses. And if we do that, well, we can exchange the sum and the expectation thanks to Minkowski inequality. And this is indeed the first step here. After that, we end up with the Q power of the sum of the Q norm of this expression into parentheses. And here we can apply Holder's inequality with parameters 1 over Q and Q minus 1 over Q in order to, certain sense, exchange the order of expectation and the integral. Here we apply Holder's inequality to the integral. And then we end up with this expression in which it appears the 2Q moment of this partial sum. But we know how to treat this because, well, first of all, if P is quite large, so close to xi, then this expression is just bounded by 1 because the partial sum of f contains at most 1 point. In the other case, the non-trivial case in which P is smaller than xi over this parameter capital X that we need still to choose, then we can use a rough Weber contracting inequality as we did before and upper bound this expectation with the Q power of a divisor sum into short intervals, for which we have a sharp estimate thanks to Schu's theorem, and then which gives this bound here, and then we can rewrite this bound in this shape since, as we said before, P is in the complementary range. Finally, choosing now the parameter X to be this power log xi, we see that here we basically have xi over log xi to the power q. And this is what we wanted, right? So collecting things together, collecting this bound with this bound, putting things back, we actually get the bound xi over log xi to the power q for this expectation, which inserted here, we showed leads to a summable bound on L. Okay, so this settles the part of the variance associated to this step. Now we need to study the main part, which is the part associated from the complete partial sum of f over this continuous condition here. Okay, so in order to do that, okay, so here I just rewrote what I said. So we are left with bounding the probability of this event, which is the supremum for test points in this range. We have this normalizing factor, and then sum over primes integral of this sum squared. And we are looking for the event, this is the event that the supremum is larger than this chosen parameter t. Okay, now again here, we will see in a moment that this looks like a martingale because a sub-martingale, because this will be rewritten in terms of a partial sum of f over smooth numbers. But here we cannot apply something like Dup's inequality not straight away to understand the probability of this event, because we are taking the soup over a very large set of test points. So this is indeed a difference between also Laut and Baum's work, in which they get to a point similar to this, and they apply Dupes inequality straight away, which is basically the best they can do. But here we have, compared to them, a much wider interval in which we take the test points, and that application of Dupes inequality will be inefficient. So the first idea is to split this interval into exponentially dyadic intervals. So saying by taking log xi between log zlj and log zlj minus 1, where zlj is this quantity, so the exponential 2 to L minus 1 power k plus j, for any j between 1 and capital JL, which is this quantity. And then we swap integral and summation and change variables to upper bound this part of this expression with, well, first this quantity, and then trivially with this other quantity in which we insert the condition on the largest prime factor. So here this condition is useless because, of course, the largest prime factor is smaller than this quantity, since we are integrating on z, which is smaller than the quantity itself. But what we would like to do is to extend further the integral between 0 and infinity, and that we keep this smooth condition here. And then we recognize that these L2 integral exactly coincide by Parseval identity with the L2 integral of a truncated Euler product associated to our random multiplicative function. So this will be called for us truncated Euler product at level j, because the primes are smaller than zlj, and I remind you that zlj is this exponential, where here we have this j translate in the phase. Okay, so now we can do what we pre-announced before. If we look at this L2 integral normalized by this factor, this forms a non-negative submertingle with respect to this filtration. So the sigma algebra generated by all the FPs for p smaller than zlj. And again, this is another difference between Lauten and Baumwood's paper, because here we have a submertingle normalized by this factor, and this actually makes this quantity a suitable submertingle for us. And this factor, I would like to remark, comes from our splitting into exponentially dyadic intervals that we did before. Okay, so at the end of all these manipulations, we are now left with bounding this event, the probability of this event, that the supremum over this short interval of j, of this normalizing factor of the integral, the two integral of the truncated Euler product is large. And here I remind you that t is epsilon times L to the power 8. So again, here we said that this L2 integral normalized by the factor 2 to the power j is a submertingle. We have a soup, so maybe we can just apply Dupes inequality to bound the probability of this event. Well, actually, this again would be too inefficient, because in Dupes inequality applied at this point will just capture the fact that the expectation of this submertingle is bounded by the logarithm of the length, which corresponds to 2 to the power L minus 1 to the power k plus j. And will not take into account of this extra factor square root L to the power k, which we have here. So we have to do something different. We have to take into account of this factor, and this is what? Is the square root of the log of the length of this integral. So this is this comes not just on the bound of the expectation of this, but from low moments results about this integral. And in order to take into account of this factor, we first assume that the integral of the truncated Euler product at level 0 is upper bounded by square root t times its expected value given by low moments result. And then we study this event conditioned on this assumption of small primes. Okay, first of all, we need to check that this assumption is okay, that we are not asking too much. And so we study the probability that the opposite holds. Well, in order to study that event, the probability of that event, we first apply Markov inequality with power 1/2. So we will get this normalizing factor to power 1/2 times the expected size of this quantity to power 1/2. And here, again, we have the 1/2 moment of this L2 integral of a truncated, the truncated random Euler product. And by low moments result that were proved by Harper some few years ago, we know that the expected size of this is exactly, or at least roughly, 2 to L minus 1 to power k, which is the logarithm of the length of the truncation here, over the square root of log of the length of the truncation, which is square root L to power k. And everything is raised to the power 1/2. So putting the Hammond's result here, we immediately get this bound 1 over t to power 1/4, which by definitions of t is bounded by 1 over L power square. And this is summable on L. So it's okay for us, for our application of Borel-Cantelli, which means that now we can really study this event by conditioning on the behavior of small primes given here. And this is what we do. Of course, as I said before, we apply Doobb's maximal inequality, and we get this upper bound. So again, we have a factor which normalize this expectation. And now we have the conditional expectation, condition on the previous event on small primes, of this integral, where we have, which is the L2 integral of the random Euler product at level J, capital JL, which is the maximal level, of course. This comes from the application of Doobb's inequality. And here I made more evident the presence of the random Euler product at level 0. And why is that? Because by properties of conditional expectation, we can insert a full expectation inside, which we can then switch with the integral and move even further inside. And now we have to deal with the expectation of the random Euler product on large primes. Indeed, this expectation coincides with the expectation of the product for primes in this interval of the square of the p Euler product factor of F. By independency of the random variables Fp for different primes P, we can switch product and expectation. And this will be the product of the expectation of the square factor, which can be easily computed at end and gives this factor 1 plus 1 over P. And this product is clearly computable by Mertens's theorem and gives this upper bound written here. If we now insert this upper bound back inside this expectation, then we will get a final final upper bound for the previous probability given by, again, this normalizing factor times the conditional expectation of this L2 integral. But we are indeed conditioning on the size of this L2 integral. And we are saying that this integral is actually bounded by the reciprocal of what you read here, times possibly a square root t factor of loss that we could have. So the upper bound for this will be 1 over square root t, which again, by definition, t will give us an upper bound of 1 over L to the power 4, which again is summable on L. And so it's sufficient for the application of Borel-Cantelli. So this concludes the proof of the theorem. And I thank you very much for your attention.
Thank you, Daniele. Thanks a lot. Okay, so are there any questions?
Yes. I'm really a beginner in these things, but your talk was rather clear. I had the feeling that you can prove a stronger theorem from the same proof if you fix some fixed multiplicative function f naught, say f naught equal mu of n or f naught equal n to the it naught. You can prove that the sum of f of n times f naught of n with the same condition is very often very large. Is that, do you think so?
Okay, so
I have the feeling that you can multiply by some fixed stuff of modulus 1.
Yeah.
Instead of multiplying by 1, you can multiply by n to the it naught, for instance.
Yeah. Well, I have to think about that, but it might be possible.
So I know that it's possible for moments. Sorry, and I wouldn't be surprised if it's not possible here, but I don't really know.
But does that mean getting a result with the absolute value? Or?
Where the absolute value?
No.
I mean, if you can, when you can multiply by anything with modulus 1, or
A multiplicative function with some bounds on prime powers and some regularity maybe on primes. But yeah, if you
okay, so like a fixed one. Okay, okay.
No, but you're right. We have to avoid the absolute value. Yeah, something somewhere.
I don't see how the absolute value could arise. It's just a fixed function, and then you have a random function.
Yeah.
Ah, yes, sure.
That was my confusion. Yeah.
Mm-hmm. Okay.
I have two questions, if I may.
Sure.
So first of all, does the argument also work in the Steinhaus case?
Yes, it does.
Okay, so why do you do it in the Rademacher? Isn't the Steinhaus case nicer?
No, it should be the same.
Because you don't, okay, fine. I mean, generally, it's technically easier because of translation invariance or something, but okay, fine. And the other question, so you explained, so we expect or essentially know that the right order of magnitude is something like square root of x times log x to the 1/4, maybe plus little of 1 or something, right? And you explained that this might be plausible because we know that for the moments, it's square root of x divided by log x to the 1/4. And so this discrepancy of 1/2 is the same as in the independent case because of the law of the iterated logarithm, right?
Yes, it's a guess.
Yeah. Is there a more concrete reason somehow why the discrepancy should be the same?
Well, what do you mean by concrete?
Well, to me, it's not obvious heuristically why the discrepancy should be the same in both cases. Is there some heuristic argument that explains that?
No, I don't have it. Well, actually, it's not at the moment really clear if this quantity here really characterizes this largest fluctuations of the partial sum of f. It's a guess based on this reasoning here that I gave here, and based on, well, the work of Adam on the lower bound, and this work I presented on this particular subset sum. But yes, you are right. It's not clear at the moment if this is really what we have for the partial sum of a Rademacher random multivariate function.
So maybe you could say that this is a remark more than a question. The one difference between the case that you're looking at here, the case of Lighting and Wu, is that because all of these numbers have one very large prime factor, you're able to use Hoeffding's inequality, which they're not able to do. And that accounts for some of the reason why your result is stronger than what they get. And if you're in a situation like that, where you can use something like Hoeffding, well, that's exactly the reason why you get this square root log-log multiplying factor in the independent case. Because in the independent case, for a sum of completely independent random signs, if you fix yourself at a point, that's what the large deviations look like. You have that kind of Gaussian tail. And using Hoeffding's inequality here, you're also saying that conditional on various things, you get that kind of Gaussian tail. Similarly, in the lower bound argument, you show that you can find a random subset of points where you have Gaussian type behavior, so you get a Gaussian tail. So the square root log-log is characteristic of a Gaussian tail coming into the argument. The reason that we don't know for the full partial sum the matching upper bound yet is because if you move away from the numbers that have a single large prime factor, it's not obvious where these Gaussian fluctuations are going to come from. So that's why the numbers with a big prime factor is an easier case than the full sum. But at least if you just look at these numbers with a big prime factor, that's the reason you get this square root log-log. It corresponds to a Gaussian tail somewhere.
Because when you condition, you have Gaussians essentially.
Yes, yes.
Yeah. Thank you.
Yeah. So it's a sort of a optimistic belief that we might still be able to find this Gaussian type behavior for the full sum based on some work in progress, but it's also, maybe it's wishful thinking. But, it's what I think anyway.
Thank you very much.
Other questions? Okay, I think I have a naive one, which is, okay, so I guess so from the beginning of the talk, you were giving results which are getting sharper and sharper close, I mean, somehow tending to square root and then something about log-log. I guess my question is about when do you think is the right moment to stop? I mean, how precise do you think we can get on this kind of results of what the average size of this thing should be?
Well, let's say, as we discussed before, optimistically, we can achieve like largest fluctuation of size, root x, log x, 1/4 plus something. And this something, well, for the upper bound, I would expect to be like this epsilon saving here, which is different from what we get from the lower bound. So I don't know, I would be surprised at the moment if we can get like this strength of result also for the upper bound.
But I guess my question would be like, okay, so suppose you, I mean, do you think, is it reasonable to expect and then also meaningful to understand better the plus epsilon there, like the further powers of log-log-log or log-log-log-log?
Yes, that's a nice question, but I don't know the answer.
I think it's a mean question that anybody from outside of analytic number 3 would ask. I mean, how many iterated logs do you want in this one?
Yes, you're right. I asked the same to myself, but I don't know the answer at the moment.
Mm-hmm.
I mean,
yeah, I think it's maybe still not the moment to ask this question. I guess right now you have this problem of of understanding whether it is actually log to the power of 4th or not.
Yeah, exactly.
And I personally think that it's interesting to know that it's definitely not the iterated logarithm, which was not so clear for quite some time.
What do you
it's
mean?
Not square root of x divided by log x to the times log sorry. Times log x to the 1/2.
Right. Any other questions? If not, let's thank the speaker again. And now I'm gonna upload via Zoom because I scared some people at my house last time.
Excuse me, I finally have a question.
Okay.
But I was thinking hard. You have a less which hides an absolute value, and you're getting large values, yes?
Yes.
And are you getting also small values? I mean, minus stuff. I mean, omega plus or minus. Because I'm just wondering whether you can cover, I mean, between the maximum and the minimum, can you cover all the values? So I was trying to build an argument telling me that because of your result, you could cover all the values. Yes. But to do that, I need to be able to go from a maximum value to -1. And so my question is whether you have a continuous between the maximum value and all the values below.
I don't know. That would be interesting to understand.
So for the lower bands, you could get large values with positive or negative sign.
Yes.
Or in the Steinhaus case, you could get large values that point in any direction you want in the complex plane.
Okay. And it would be possible to get it for the same function? I mean, to get both of the same. I would like to know whether you can reach any value between square root log x square and no, to the 1/4 and minus square root of log x to the -1/4.
Well,
so if I get it for the same function, I can use some continuity argument. Maybe I can work it out.
Yeah, so I mean, the lower bounds would say that almost surely, so for 100% of realizations in the random function, you'll have points where the sum is like root x log of x to the 1/4, and you'll have points where it's like minus root x log of x to the 1/4.
So I can make an intersection, but then I need this axis to be close enough.
Yeah, so you'll find some points on intervals between capital X and capital X squared, let's say, where you'd have the large positive and negative values.
And then we should be able to cover, if it's between x and x squared, it's not so far away. Okay. Okay, thank you. Sorry, I was muted. I'm over.
All right. Yeah, I don't know if the last one counted, so I'm gonna thank the speaker.
So we thank the speaker and bye.
Yeah, I'll clap virtually again because of people in my house. Thank you, Daniele.
Thank you.
Thanks, everyone. Okay, something on the chat. Okay, so next week we have Chris Hughes from the University of York. The title abstract is already on research seminars, and then we pause for the Easter break, and then hopefully, I mean, we're still filling the dates. I said, oh, I have to stop the recording actually. Wait, I'm not the host anymore.